I want to thank you for having me over on this. Great set of presentations before me. One of the earlier presentations, in fact, luckily has set the stage for my presentation, what I was going to discuss when we mentioned the taxonomy of logged attention. So here I'm going to present log attention. It's a methodology that a software engineering manager can use to assess the health of a release based on anomaly detection using runtime logs. I actually work for Dubai Development Authority. It's a very dynamic organization, forward-looking, where we develop multiple services, products to be used in the government and by the citizens in Dubai. And certainly, like anybody else, we face a lot of challenges when we deploy these services, when we deploy microservices and multiple microservices across multiple products. So we were looking at, and as I go in this discussion further, so we were actually looking at evaluating various methods where a software engineering manager can be sure of the quality of the release, of the health of a software release. We know that modern day software is built on cloud native microservices based distributed applications. They produce a huge volume of logs, and just the sheer volume of logs make it impossible to use these logs as a preemptive tool or a prediction tool. We only typically use these logs as a forensic tool. And we also know that during runtime, no matter what amount of pre-release testing you do using static analysis tools, most of your faults happen at runtime. You have to shift right on your testing because of dynamic late binding of services. These runtime faults cannot be detected by any amount of pre-release testing. So certainly, as one of the earlier speakers said, that there are three viable sources: logs, traces, metrics that you can look at. So we saw log as a viable source of this runtime information. We wanted to see how we can have a very small set of logs and what techniques can be implemented to be able to look at a very small set of logs that gives us meaningful insights. So that's where this effort started when we were working on this. Me and my colleagues who are actually attending the session here, Hamid Ali and Jahangeer Qureshi, who are my co-authors in this research. So we looked at the problem statement where a software engineering manager must identify faults in production to predict and preempt failure, which is challenging given the available tools and techniques. And we wanted to see if we can develop a machine learning methodology based on detecting anomalous log messages to give actionable insight to the software engineering manager. So we have various techniques that are available for anomalous log messages. The idea was to see if those anomalous log messages are remarkable, do actually indicate a potential failure in production. So the research objective here was to devise a methodology that is capable of providing a snapshot of the health of the release in production to the software engineering manager. The task is difficult because of the variance in logs that is coming out of multiple systems, multiple microservices. And so we looked at multiple approaches. We wanted to answer the research questions that can machine learning be used to analyze runtime logs to assess software release quality? Can machine learning based log anomaly detection provide insights from runtime logs to preempt a failure in production? Once we do that, these anomalies that we have identified, do they correlate to issues in production? I'm not saying that they are the cause. Causation is not correlation, but do they actually correlate? And then the next step was, can we look at transformer-based language models? Can we consider the logs as the corpus? And can we use transformer models to detect anomalies in these logs. And last but not least, how much data would need to be labeled for anomaly detection to identify anomalous logs accurately? So these were some of the questions which we're looking at. And we had the hypothesis that we can use machine learning, log messages will correlate with issues reported in production. And most importantly, we looked at that you need a very small subset of the log data, 20% or less, to be labeled in order to get accurate results with any supervised technique. So these were some of the things which we were looking at, research questions we were looking at. The scope of this research is to assess the quality of a software release in production, relevant to basically microservices. We did not want to develop a new methodology of collecting data. It could only be logs, metrics, or traces, which is already available. So we were not developing any new techniques. And the idea was to have a tool which can provide actionable insights to predict and preempt failure. Some important literature which we actually looked at, this paper from Nedelkowski, and I see probably is in the audience. So that is interesting. The new log paper, which basically was a transformer-based architecture for log parsing. So they have done a great survey on the existing parsers that are available. There are some techniques which we looked at and we are comparing. These were the state of the art, which we are comparing our model against. One is deep log, which models log sequences and identified logs as remarkable if they do not follow normal program. Log anomaly and robust log, which is, so these are some of the techniques which we're comparing against. I'll move on to the next slide. So we basically were going to use state-of-the-art log parsers to parse the raw logs. So runtime logs, we send it to log parsing, and then we use existing log parser. One of the limitations we were doing was something that is available as open source. And then that's where our model comes in. It was a hybrid model where we would have two unsupervised approaches. One is weak classification, and I'll go on the details on that. And the other is an unsupervised anomaly detection module, which is going to use pre-trained. And then the third technique is using a pre-trained supervised anomaly detector. The outputs of these three modules is going to go into the ensemble model. Ensemble model is going to, so log parser is going to give structured logs to weak classification module, unsupervised module, and supervised anomaly detection module. And then ensemble log is going to provide remarkable logs to the dashboard, and weighted logs will go to the release scoring model, which will provide a score of the health of the release to the engineering manager. Now, I will go into details in the following slides. So these are then used to compute basically a release score, which would give a snapshot of the overall health of the system, as well as these anomalous log messages will be presented to the engineering manager, a very small subset of log messages, where then she can look at these log messages to use them as a predictive tool. Maybe we can even connect this with Stack Overflow or other. So when you have these log messages coming in, so actually meaningful insights could be provided to the engineering manager. And last but not least, there is the human in the loop module, which basically provides experts who are already in that system, your senior developers, to actually tag a subset of logs and provide that input to the supervised anomaly detection module, to fine-tune the supervised module. While at the same time, the engineering manager could be looking at the remarkable logs presented to her and maybe reclassify them and provide that as the input to the supervised module. So this is the model that we have developed, and I'll go into details in the following slides. Just a snapshot of one UI that we built for this here. So it will give you a release score, and it will give you interpretation of that score based on your product that you're using it on. How many total logs were evaluated and the remarkable logs. So the remarkable log percentage is going to be very, very small. And then the next step is probably, the video is not playing, that's okay, where it can provide details of those logs, and maybe the manager can click on it, see the logs before or after it, and so on and so forth. So various implementations could be done of this module, of this model, which one of them I'm showing here. So on the log parsing side, a log parser basically essentially parses an unstructured log into a structured one, and basically it extracts event template parameters. So it would give you timestamp, log level, the event template, and the parameters. For this study, we are using drain and new log as our parsers. In fact, this metric from this paper of Nedelkowski, self-supervised log parsing, we looked at various, which basically evaluates various log parsers for their parsing accuracy. And drain and new log were those which we preferred. Again, their code was available as open source. We found these of interest, where drain is a log structure heuristic-based parsing model, whereas new log is a neural network-based log parser. And they demonstrated impressive performance even in our tests when we were looking at it. We had some cases where on large log files, new log was outperforming drain. But the bottom line is that you can use any log parser, and based initially, it maybe the engineering manager can use one of these, but eventually in her environment, she could be evaluating various log parsers, and we basically would have a burn-in period where you can evaluate these log, what works best in your product environment. On the weak classification module, we used 3 weak classifiers. One is basically an error lexicon classifier. We scraped logs from popular GitHub repositories and made a list of high incidence errors. We used this dictionary to find potentially remarkable events in the runtime data. Then there was a log level classifier, which simply uses inherent log levels, which are more important. Warning, warning is not important. And the third classifier basically is a double sigma classifier, which computes the time delta between 2 log events and tags it as anomalous if it is beyond 2 sigmas of the rest of the logs. So this is basically just a very simple heuristic-based model initially, so that the tool is going to work in a zero-shot capacity. No learning has happened. It is starting, so we can give some weightage to the weak classification module. The next step was an unsupervised anomaly detection module. We are using DistilBERT, which is a smaller variant of BERT, and use the embeddings to classify anomalous log messages using self-organizing maps and isolation forest. What we did was we evaluated various embeddings and classifiers against our data set. So SEA and DNC. SEA, I'll explain further, is a product. These are 2 products which we are using in my organization, and there are multiple releases which we are evaluating it against. So we saw that DistilBERT was one of the best embeddings that we saw, and the best classifiers that were performing were SORM and isolation forest. So we decided to use both of them to classify and send the results to the Ensemble log. On the supervised anomaly detection, we used Electra. Again, we evaluated against multiple mod embeddings and multiple classifiers. And we found Electra as something performing very well. So we used it to train the log data. So in the first phase of semi-supervised learning, your aggregated log data will come to the language model of Electra, which is going to predict the masked word. It's basically using masked language modeling. Then we take this as in the supervised learning phase, where tag data is fed to the language model from phase 1, and embeddings are sent to a classification head. Object is to learn and classify log messages. Then the third inference phase, where structured logs from the log parser are going to this language model from step 2, and embeddings are going to the classification head, which is going to provide classified logs to the Ensemble model. So this is what we used basically. So the Ensemble model would look something like this, where the outputs of classified logs from the weak classification module, unsupervised and supervised, will be fed to the ensemble module. And these are weighted logs from all of these modules, would be combined using predefined weight, or the software engineering manager is going to update the weights. The tag data will update the weights. And we are also in the next phase of the research looking at building a self-optimization model. Now, initially, when we start, the WC module would have higher weights, but once the tagging is done, the weights of weak classification is going to be very less, and supervised module would have the highest weight. So again, this is a way that it is going to work even in a zero-shot capacity. Now, the last but not the least, we developed a human-in-the-loop module, which we kind of tweaked. We looked at a lot of research and realized that when we are basically tagging the data, we should basically be looking at a combination of random sampling, marginal sampling, where these are at the edges, and the certainty sampling, where the data points we are very certain about. So a combination of this would be best to curate a log data set, which then goes to the tagging interface where a senior programmer or a senior developer is going to tag. And in our evaluation, we saw it would be best if we give equal budget to random samples, marginal samples, and certainty samples on this. So the weighted logs goes to a release scoring module. This is how we are comparing the release with other releases, the past releases of the. Sorry?
We lost you.
Okay.
Okay.
Am I here now?
Yeah, we can hear you now well.
Okay, great. So, so basically, here it is that how this release compares with other releases of the application, and how many anomalous logs were observed in this release. So we compute this variable by comparing the prevalence of the current release with the prevalence of the best versions among the previous releases. And we then would like to optimize the selection of weights in future, and where we will put this feedback loop as well. So currently the ensemble model goes to the release model. Here, what we are doing is we are looking at which is the circle overbar, underbar is basically the symbol for LogAttention for the score for the ith release. L is the set of log messages for the ith release. Then R is the set of remarkable or high priority log message for the ith release. Then we have M, which is the medium priority, and O, which is the low priority log messages. And we have weights assigned to the high priority, medium priority, and low priority log messages, whereas WP is the minimum detection prevalence. So this basically model gives us the score of a release. And next stage is, so the data sources that we were using for this research, there's a product called Smart Employee, which basically is the HR, the front end for a web app for the HRMS that we use for the government of Dubai. It has 56,000 active users, and we evaluated around 12 releases that were in 2020, about 2.6 million log messages. So we selected 4 releases for our testing, and 2 of the releases we selected randomly for tagging for our results. The other product is Dubai Now, which has over 100,000 active users. It has 1 million downloads. It's a mobile app for city services in Dubai. And we looked at 21 releases in 2020, 500,000 log messages. Out of this, we selected 1 randomly, which we tagged. In addition to this, we also created a Flamingo e-commerce server, sent simulated data to it. We could use Selenium to generate log products, computers, clothing. We put some products there so that the users were selling, doing e-commerce transactions. And we introduced on purpose 3% logs randomly by randomly disabling 3% faults, by randomly disabling search interface. So we generated 10,000 logs, 330 were anomalous. The prevalence was 3.1%. In addition, we just wanted to try this model, not very significant, but we use syslog and BGL data sets to also test these models. BGL is a very common, famous data set that is used. We had 100,000 log and 2,600 were anomalous. Okay. So we wanted to use some public data sets also to benchmark against. Results are not important. For just a refresher, because I'm going to show the results. So I'm going to use precision, which basically is how many remarkable logs were relevant, recall how many relevant logs were classified as relevant, and F1 score, which basically is high when both negative and positive, false negatives and false positives are low. So just wanted to just refresh everyone and give a evaluation metrics 101 to everyone. What we also like is Matthews correlation coefficient, which basically is class agnostic. I will also show the results of ROC. So ROC, the ideal curve, optimal curve is here, which is 1, and anything above this line is, which is a naive classifier, coin toss. So anything above that is good, and optimal is here. So an area under the curve is area under this curve, this gray blue area, which is between 0.9 to 1, it would be excellent. So now I was comparing, we actually compared our LogAttention module for the green is smart employee data set, 2 data sets, Dubai Now data set, and this one is Flamingo. So we evaluated this against deep log, log anomaly, then LogAttention with just unsupervised anomaly detection with weak classification. Then there is a supervised technique called robust log, and we evaluated it without training and with training. With training, robust log was performing very well, and LogAttention, the precision was near 1. Same is the case. Recall, the recall was very, very high. Robust log with full training had better recall. Then we were looking at macro F1 score, and certainly deep log and log anomaly were unsupervised techniques. LogAttention unsupervised was still performing better than deep log and log anomaly. And LogAttention with all of the modules active was performing much better than any of the techniques. And of course, robust log, while when it was trained, is performing very well. But the issue with just using a supervised technique and not an ensemble model is that before it is fully trained, the performance is going to be very bad. And similar observations were there for MCC. The next evaluation was to see the area under the curve. And again, we were near perfect in all 3 cases. We also saw that, okay, we also wanted to evaluate the effect of training. How much data, how much log data should be trained in order to get very good results? So we evaluated LogAttention with just unsupervised anomaly detection. These are the F1 scores with supervised anomaly detection plus weak classification. Then having LogAttention trained with just 10% random data, and LogAttention trained with 20% random data. And then we had LogAttention trained with 10% curated data that the technique that I told you of, marginal sampling, certainty sampling, and random sampling, the 1/3 each, and with 20% training data. So we saw that number 1, with human in the loop module, with our technique, we were actually of training of curating data set, we were getting slightly better results. And even with 10% training, you were getting very good results here. Another very important thing was detection prevalence. In case of log attention, it is significantly lower when we compare to log anomaly and deep log, which means that the engineering manager has to go through a very small subset of logs in order to get meaningful insights. So in case of log attention, we are talking about across data sets, 0.03%, 0.03% for these two data sets, 0.01% for the buy now, versus much higher, almost an order of magnitude higher detection prevalence for log anomaly and deep log. This was very interesting. We said, okay, we see remarkable logs. How do we see that they actually mean that there's a potential quality issue in the release? So we chose releases where there were a lot of issues that were reported in Jira. We looked at the Jira data and see that does the score correlate with when we see more issues reporting in Jira, indicating more buggy release, more issues being reported after the release. So we certainly, the data is not enough to prove or disprove any hypothesis here, but the findings were very interesting. With certainly with more data, we can yield even better results. However, one thing is interesting, that after 20 hours of training, you see very good correlation in so this green line is for smart employee product, blue line is for the buy now product. And the idea is between Jira issues and this quality score, how much is the correlation? So the correlation is around 0.8, after 10 hours of training. After 20 hours of training, it gets much better. And your p-value decrease goes to below pretty much 0.5. This is 0.5 line, this is 0.1 line. So the p-value is kind of going around 0.1, which shows, again, it is not enough to prove a hypothesis, but it shows very good correlation between Jira issues. And just to show that with a random score model, there is no release correlation. So with our model, of course, we were seeing much better that there is certainly value to research further in this space. Some of the observations that we saw that log attention is an attention-based model that helps EM to assess release quality, high correlation of release score with issue score after processing almost half a days of logs. That's what we saw. We saw that a detection prevalence of less than 3% across data sets is required. The log attention identifies remarkable log messages that point a potential cause of failure. So we saw high precision shows remarkable logs correctly identify anomalies. Anomalous log message, we kind of in a way concluded correlate with issues reported in production. Log anomaly detection using embeddings from transformer-based language model outperforms other techniques. Log attention requires less than 20% of total log data to be tagged. In most cases, less than 10% to yield perfect results. So certainly logs need attention. Log attention release score potentially predicts failure. It gives actionable insights to help preempt failure. Log attention achieves perfect level of accuracy with just a fraction of the label data. It outperforms current semi-supervised and supervised LAD modules. A lot of that is because we are ensembling semi-supervised and supervised models. Log attention can provide good results in a zero-shot capacity in a new production environment, just with the weak classification. So some of the future work and contributions to the body of knowledge, we were using embeddings for language model. There's not much, if any, literature there. We use heuristic-based weak classifier. We did a lot of work on this MCR sampling, marginal certainty, and random sampling. We did some work on correlation with issue tracker data. So some of the future directions that we are looking at is, number one, include traces. So instead of logs, this is microservices environment, look at traces, doing work on incremental learning and time series modeling. And the last is we are also doing some evaluation on what if we don't parse. We do not give structured logs. Because it is a language model that we're using, so why don't we feed unstructured log and have a parserless log implementation module? So this is some of the future work that we are actually looking at. That's pretty much it from my side. Thank you.
Yeah. Thank you very much for this very nice and interesting presentation. So really interesting and cool work. So because we are quite tight on schedule, maybe one question will be, yeah, please, Professor Ode.
And I'll also have my colleague Hamid join in if there is any need. Hamid, you can unmute.
Yeah. Okay.
Yes, sir.
So hi, thank you very much for a great talk. I was really jealous of the data that you have. So it's really great to see how you do this and you get really the best out of it. So congratulations. Just one question that you mentioned perfect results on the last slides, on the slides prior conclusions. This perfect results refers that you are recognizing everything what was in the set, but you still cannot deal with unknown log messages, or do you also recognize it's open world set that you can also refer to perfect results? I mean, just to clarify, we made the experience here in our lab. We got perfect results in the lab, so once we got out to real data sets, there was a lot of noise in it, and that spoiled our results. So I wonder if you can deal with that problem.
So, you know, I agree that the moment I say perfect result, I invalidate my entire research, because we are trained to understand that there should be no perfect results, right? So, you know, here in this particular case, this was a product, known product. We have done some, you know, we know this is going to be learning on the corpus of the same product, the past logs of the same product. Mm-hmm. So you're not going to get a lot of new messages, and those are potentially anomalies. Certainly, we have not looked at training it on another product and running it on another product. Certainly, that is going to cause a lot of what you actually were saying right now. Hamid, would you like to add on that?
Yes, sir. Hi, everyone. So, yes, I think that's an excellent point. And that is, in fact, why we proposed a hybrid approach where you have the USD and the weak supervisors helping out the supervised module. And that is the burn-in period in which the supervised models will actually get up to the point where they're performing really well on those data sets. But initially, yes, we need that support from the unsupervised modules.
Thank you very much. So if you're interested, I would be very much into a collaboration on this, because I think
we would love to do that.
Okay.
Because see, we are not an academic body. We are more of a, you know, development center. Mm-hmm. So certainly I would love to do that.
But you are on the source, so I was impressed. I was impressed in the results. Maybe we can join via Yasmin later and see how
certainly, we look forward to that.
Yeah, perfect. Thank you very much, Sohail and Hamid and everyone else. Thank you very much for a great talk.
Yeah.